Hello and welcome to my channel. Here with me Ziad Ibrahim. Okay, now I need to continue in sensor fusion course, architecture, algorithms and application of this sensor fusion. And now I need to talk about the principle of inertial navigation. Okay, principles of inertial navigation. Okay, suppose that we have a vehicle like now, and we have this accelerometer sensor which measure the acceleration along this body of this vehicle. Okay, so we have this accelerometer here, and this is the vehicle, and this is the top view of this vehicle. Okay, and this is the x-axis of inertial. This is the inertial axis. Okay, and we have this a will be ax, this acceleration of this accelerometer. Okay, our assumption here is the accelerometer aligned with inertial axis, which means that there's no rotation about the z-axis. We have this acceleration along this x axis, and we need to use the principle of inertial navigation. Okay, so what we have here, we have this. If we make an integration of this parameter here of this acceleration, we'll get the velocity along this x-axis. Okay, and if we make another integration with respect to time here and here, we'll get the position in the x-axis. Okay, x inertial axis. We'll get px. So this position, and this is the velocity. The integration here from minus infinity to some time t, and from minus infinity to some time t. Okay. Okay, let's write it again here with, I need to make some initial conditions of what? Of Vx at time 0 and Px at time 0. So this will change to, we have Ax, the same quantity of this, and we make this integration with respect to time. But now from 0 to t, we need to make a sum here, because we have Vx at time 0. So we have this initial condition, and we make another integration with respect to time, but from 0 to some time t. And here we need to add the px at time 0, and now we get the px. Okay, this is the px here, and this is the vx. So here we have px, and here we have vx. Okay, so this, when we implement the initial condition, be changing like this. So we have accelerometer, which is inertial sensor. Now we assume that we have no rotation about the axis, we have just in this axis direction. So we make integration, double integration of this acceleration, we get the velocity for first integration, and we integrated second time, we get the position in x-axis. Okay, now we complete this section. We need to solve the accelerometer alignment meant if we see this vehicle or this car, and we have this case, this is the inertial axis, x inertial axis, but this car in this example is rotating in counterclockwise direction, so the acceleration in the body axis, which the accelerometer will measure, so the accelerometer, it's fixed in the body, it's fixed in the vehicle, so it measures in the body axis. This is AX, okay, in body axis, okay. So we need to see this AX in the inertial axis, so this will equal, for example, this the psi angle, which is the yaw, so we have AX times cosine this angle, which is psi, okay. So this is inertial axis acceleration, inertial axis acceleration, okay. Now we go for 2D axis transformation. 2D axis transforms. Okay, now we have the same like the previous example. We have this x inertial axis, and we have, which is perpendicular this one, which is y, and this inertial axis too, inertial axis, and we have this is the body, this axis is along the is pointing to the front of the vehicle, and this one is perpendicular to this one. So this is the body axis, this one and this one is the body axis, and this one is the inertial axis, okay. So we have here AX and AY, okay, and we have this angle will be psi, so this will be the same angle like this one, and we need to find AX, the acceleration in inertial x, which is AX cosine psi, and we have here same this, we have AX sine psi, okay. So we neglect this, we have this one, we have AY cosine psi, and we have here AY sine psi, okay. We neglect this one, so these together will be AY, the acceleration in inertial in y inertial axis, okay. So we have here AX will be equal to AX cosine psi, AX, which is the acceleration in the body axis, and this will be measured from the accelerometer, okay, directly from the accelerometer, and we have here cosine psi minus, because the opposite direction here, AY sine psi, and we have AY will be equal, these two adding together because in the same direction, AY will be equal to AX x sine psi plus AY cosine psi, Okay. We can write it again in the form of matrices. So we have ax and ay. This vector will equal to some matrix, which is called transformation matrix, times ax and ay, which is the input. And these two parameters are measured directly from the accelerometer, which is fixed in the body. So these two, I mean ax and ay, this vector, acceleration in the body axis, in the body axis. Okay, and this one is the acceleration in inertial axis. So we have here ax will be times cosine psi, and this minus sine psi, because this times this one, and we have this ax times sine psi, plus cosine psi, which is cosine psi. Okay, so this matrix is called transformation matrix, transformation matrix, which transforms from the body axis to inertial axis. Okay. Let me write it in some other way. We have a block here. We have cosine psi minus sine psi, and we have sine psi and cosine psi. The input for this block will be ax and ay, which is two accelerations measured from the accelerometer, which is fixed in the body axis, and we have an angle will be psi, okay, which is the measured yaw angle, measured yaw angle. And we have here ax and ay, which is in inertial frame. We call this inertial frame accelerations. Okay, so we make this transformation, we get these inputs from the sensors, and we make this computation inside the computer, in computer like Raspberry Pi or advanced microcontrollers, which make which makes this computation and this multiplication. And maybe you can use microcontroller for this. Okay. Let's talk a little about this this psi angle. We talk about some measurements like accelerometer, but there's another sensor which will be using this this topic, which is the rate gyro or gyroscope. So we have the output from this sensor, which is fixed in the body axis, and we make the integration for this with respect to time from 0 to some time t, and we don't forget the initial condition, which is psi 0 at time 0, initial yaw angle, and we got psi plus, we got psi, which is yaw angle. So we have yaw rate here, and we have yaw angle here. Okay, we make an integration for this. Okay, now let me draw it again. We have a block here, which is the direction, which is cosine psi minus sine psi. And sine psi here and cosine psi here. Okay, this matrix, it takes the integration of what? Of omega, which is yaw rate, and we have the initial condition, which is psi at time 0, and two inputs here, which is ax and ay, which is these body axis accelerations. Okay, we got ax and ay, which is acceleration in the inertial frame. We make integration for these two quantity with respect to time, and we add plus here, and once again plus. We have Vx at time 0 and Vy at time 0. So we got here Vx and Vy. We make another integration for these two quantities with respect to time, and we got don't forget again here the initial condition, which is Px at time 0, and plus here and plus again here, which is Py at time 0. So we got here Px and here Py. Okay, let me extend this a little bit. Should we have here Px and we have here Py. Okay, these are initial condition for position, and this initial condition for velocity, and this initial condition for the yaw angle. So all these this block is inside the computer, okay, which is the inertial navigation system, and we call this system is strapdown inertial navigation. Okay, in the next lecture we will see how to use the Kalman filter with GPS and INS. Okay, just I need to make a little bit about GPS, INS, the comparison between these two. GPS is a global positioning system, and we have inertial navigation system. Okay, we have for GPS we have low data rate, but here we have high data rate. Okay, and we have a direct position measure here and direct velocity measure here in the GPS, but no attitude information here. All quantities are measured in navigation frame, all this with respect to GPS. But INS, we have high data rate, and we have indirect position and velocity estimate, and we can estimate also the attitude for the vehicle, and all these quantities are measured in the body frame because we dealing with sensors which is fixed in the body. And we'll see in next lecture how to use the Kalman filter with these two to get a best estimate and used in navigation system. Okay, thank you for watching. See you next time.